Welcome to the Explainer. Today, we're conquering a massive concept in computer science, dynamic programming, and we're going to do it by evolving a solution to the absolute classic, the climbing stairs problem. We'll take it step by step, literally. If you've ever felt completely overwhelmed by DP, well, you're in exactly the right place. We're going to break this down so logically, it'll just become second nature.
So here's our roadmap for today. First, the climbing stairs problem itself. Second, our top-down approach. Third, memoization to save time. Fourth, building it bottom-up. Fifth, the ultimate space optimization. And finally, number 6, the interview playbook. We're following the exact evolution you'd want to use in a real technical interview.
All right, section 1, the climbing stairs problem. How many ways to the top? Let's just dive right into the core challenge we're facing today.
How many distinct ways can you climb a staircase of n steps, taking either 1 or 2 steps at a time? I mean, it sounds like a totally simple math riddle, right? But this specific problem perfectly illustrates why dynamic programming is notoriously tricky. The possibilities just branch out incredibly fast.
Just look at how the distinct paths explode for a tiny 4-step staircase. You could just plot along 1, 1, 1, 1, or take a 2-stepper, then 1, or maybe 1, 2, 1. You get the idea. Even for just n equals 4, you've already got 5 distinct ways to reach the top. You can imagine how wild these combinations get as the staircase gets taller. It proves this isn't as simple as it first sounds. We absolutely need a systematic way to solve this.
Moving on to section 2, top-down, breaking it down, building our intuition. Let's establish how to actually wrap our heads around this. Now, this is the crucial part, the optimal substructure. Think about how to actually land on a specific step. Let's call it step I. Since the rules say you can only take 1 or 2 steps at a time, you literally must come from either 1 step below it, step I-1, or 2 steps below it, step I-2. That's a hard physical rule. There's just no other way to get to step I. And honestly, that's all the information we need. If we want to find all the different ways to get to step I, we just add up the ways to get to step I-1 and the ways to get to step I-2. We can translate this optimal substructure directly into our recurrence relation, climbing stairs of n equals climbing stairs of n-1 plus climbing stairs of n-2. To code this up recursively, we just need our base cases. Super simple. If n equals 1, return 1. If n equals 2, return 2. Boom! Done!
Okay, section 3, memoization, saving time, solving the overlapping subproblems. So we have a working recursive formula, right? But if we run this blindly, we hit a massive performance bottleneck. Let's fix that. Just look at the brute force recursion tree for a tiny staircase of 6 steps. It starts from the main problem at the top and recursively shatters into smaller and smaller subproblems. But do you notice the massive repetition? To solve for step 6, we need 5 and 4. But to solve for 5, we also need 4 and 3. We end up calculating the exact same subproblems, like step 4 and step 3, multiple times across completely different branches. For a tall staircase, this overlapping subproblem issue is an absolute nightmare. It's a huge waste of CPU time. To kill this repeated work, we pull out a magic weapon, memoization. Memoization is just the practice of storing the result of each subproblem the very first time we solve it. We typically toss this into a hash map for instant, constant time access. The step number n becomes our key, and the calculated answer is our value.
So here is the real game changer. By fetching these already calculated results, we completely prune the recursion tree. See the green dashed arrows here? The very first time we calculate step 4 on the left side, we save it. Then, when the computer realizes it needs step 4 again over on the right side of the tree, it doesn't recalculate a single thing. It just instantly fetches it from our hash map. We completely save ourselves from all that redundant math. The impact of this is honestly incredible. Without memorization, our brute force approach had a terrifying time complexity of O of 2 to the power of n, because the tree branches out by a factor of 2 at every single step. It is literally an exponential nightmare. But with memorization, we ensure every single subproblem is solved exactly once. By just remembering what we've already done, we take our time complexity from that exponential curve all the way down to a beautifully streamlined linear O of n.
Which brings us to section 4, bottom up, building it up. Translating recursion to tabulation. Now we solved the time issue, but our recursive call stack is still eating up ON memory space as it grows. So let's evolve this into a bottom-up approach.
Here's a golden rule. Generally, any problem you solve using top-down memoization can be flipped into a bottom-up dynamic programming approach. Think about what our memoization hash map was doing. It was just storing the answers to subproblems, right? Well, we can just use an array, let's call it DP, to do the exact same thing. Because it's a one-to-one mapping, we can literally just swap the word memo for DP. But here's the trick. Instead of starting at n and recursing all the way down, we started our base cases, steps 1 and 2, and calculate the smaller subproblems first. We iteratively build up to our main solution, and we never even trigger a recursive stack.
Next up, Section 5, the ultimate space optimization, reaching O1 space. We made it fast with ON time, we removed the recursive stack, but hold on. Our DP array is still using ON memory space to store the answer for every single step. Time for our final optimization.
Look really closely at the DP relation we just built. To calculate the current step I, what do we actually need? We only ever need to access the previous two values. That's it. We absolutely do not need to store the entire historical array. We can literally just use two variables, one step before and 2 steps before. As we loop through the steps to build our solution, we just update these two variables. They essentially slide forward, always holding the values for the immediate previous 2 steps.
This elegant two-variable sliding window is the absolute optimal state for this problem. It keeps our super fast linear ON time complexity since we're still just iterating through the steps once, but the space complexity, we reduce it down to an absolutely perfect constant O of 1. Think about that. We went from an exponential, memory-hogging brute force monster to a ridiculously efficient constant space algorithm.
Finally, Section 6, the interview playbook, how to apply this strategy. Let's wrap this up by looking at exactly how you can use this progression in your next whiteboard interview.
This quote is pure gold from our source material. In an interview setting, staring at a blank whiteboard and trying to instantly conjure the perfect, bottom-up optimized solution, it's paralyzing. Don't even try it. Start top-down. Identify the recurrence relation first. It is so much easier and more intuitive to just break the main problem into smaller chunks. Once you have that, slap on some memoization to optimize it. Got that working? Great. Now you can confidently map that exact same logic to a bottom-up tabular format. And finally, look for space optimizations like our 2 sliding variables. Eventually, you'll get so good at this mapping you might skip the top-down step entirely. But seriously, it is always your most reliable safety net.
And there you have it. We took the climbing stairs problem and used it to totally demystify the dynamic programming process. By understanding how to spot optimal substructure, kill repeated work with memoization, and shift from recursive to bottom-up iterative approaches, you've just equipped yourself with a massive conceptual toolkit. So the question is, now that you've mastered the optimal substructure of climbing stairs, what other dynamic programming monsters are you going to conquer with this exact same top-down to bottom-up playbook? I hope this explainer leaves you eager to hit the keyboard and find out. Thanks for joining us.